All right, example 4. Ambient air pressure at sea level is generally about 1 times 10 to the 5th pascals. So if we have a cylinder with a radius of r equal to 0.035 meters and a height equal to 0.17 meters, so that's just about the size of a smallish soda bottle, and we managed to create a pure vacuum inside of it, and real quick note, actually impossible to create a pure vacuum, at least as far as science has figured out to do so far. Laboratory vacuums have never managed to be perfectly pure. It gets harder and harder to suck out the last thing. Just imagine if you're trying to suck all the dirt out of a carpet. It's easy at first, but those very, very last few grains get really difficult because it can give it kind of hard to catch those last few because they've got so much, it's harder to get at those very last few because there's a difference in the pressure that you're trying to pull at it with. Not exactly a perfect metaphor with the dirty carpet, but hopefully understood. So if we want to figure out what the force of the air pushing on this bottle will be once there's no air inside, because normally we've got air pressure, we open a bottle, we've got air pressure inside of the bottle, we've got air pressure outside of the bottle. So there's no difference because they're both being pushed on by the exact same amount of air pressure, so we'll see no deformation. We've got static equilibrium. Same amount of pressure on one side as the other side, so no change is going to happen. If we've got the forces canceled out, we've got the pressures canceled out, nothing happens. But if we manage to make a perfect vacuum, suddenly there's going to be all that force of air pressure pushing down on it, and there'll be nothing to resist it with. And so we're going to actually see some really big changes. So first we have to figure out how much area does the air pressure have to push with. So we need to figure out what's the surface area of that cylinder. So the surface area, what are the two ends of our cylinder? Each end of our cylinder is pi r squared. How many ends do we have? Well, we've got two ends, so 2 times pi r squared, plus what's the area of the outside of the cylinder? Well, the length of the outside of the cylinder, a cross-section length, is just the circumference of a circle, 2 pi r, or the diameter times pi. And then if we want to figure out what the total area is, we slide that down, and it slides down by height, and so the swept area is going to be that circumference times the height that it sweeps through, 2 pi r times height. We substitute everything in. We've got 2 times pi times 0.035 squared plus 2 times pi times 0.035 times the height of 0.17. We toss that all in together, put it into a calculator, and we get that the total surface area our bottle has exposed, or our cylinder has exposed to the air, is 0.0451 square meters. So if we want to figure out what the force pushing on that was, we want to look at what's the pressure. Well, we know pressure is equal to force over area. We know what the pressure is here. We know what the area is, so we just toss those two together. We have that the area times the pressure is equal to the force. We plug in the area. We know our area is 0.0451 meters squared times the pressure, which is 10 to the 5th pascals. Multiply those two together, and that's equal to 4,510 newtons, which is a whole lot of force. I mean, imagine how much force that is. That's enough force to lift about 460 kilograms. If you can lift about 460 kilograms, that's enough to be able to pick a motorcycle up off the ground and lift it over your head. If you have enough strength to do that, if that's the amount of push that you're putting on this cylinder, that you're pushing on a soda bottle, it's just going to absolutely crush. There's huge amounts of pressure, and that's why when we take a soda bottle and we go underwater with it and we look at it, it gets deformed by even just like 1 meter of water. It gets reasonably deformed because it crushes, because there's massive amounts of pressure in there, and that is with air pressure already inside the bottle. If you've ever put a soda bottle to your mouth and sucked the air out, you've been able to use muscle expansion in your chest to change the pressure differential in your lungs so that some of the air in the bottle comes into your lungs. You've seen it squeeze down just a little bit. You've changed it by like 10–20% of the internal pressure. Probably way, way less, actually, now that I think about it. You're changing the internal amount of pressure by very, very little. And that change, that small change, is able to cause massive crushing. Imagine if we were to have a perfect vacuum. We'd just smash that bottle. And this also is the reason why straws work. If you've ever taken a straw and put it into a simplified drawing of a liquid, If you manage to suck out some of the air pressure in here, then all of the air pressure of the water, all of the air pressure of the air is going to push on our liquid, and it's going to push that drink up our straw. However, if you want to prove that it's air pressure and not suction that's causing it to come up, which a lot of people think at first that it's suction in the straw, take a straw, suck up some amount of liquid into the straw. Now, take the bottom end and pinch it off. So take a straw and then fold it up and hold it pinched. So you've still got some liquid inside of it, and now try to suck out of that straw. If you try to suck out of that straw, you're going to notice the water won't come up to your lips because you don't have enough strength in your lungs to be able to crush that whole thing, because you'd have to put a huge amount of anti-pressure there. You'd have to create pretty much a vacuum inside of that, and you can't create enough vacuum with just your lungs. That's just not by a long shot enough mechanical power to beat the pressure of the air. You're going to have no way of being able to pull that liquid from that straw into your mouth. And so what we know, the reason why a straw works is because we've got all this air pressure around us. We're lowering the air pressure inside of the straw, and so there's now this differential in pressure, and the water, the liquid, whatever our drink is, gets pushed through the straw because air pressure is pushing down on the rest of the drink. That's why it works. So pressure is absolutely amazing thing. Huge amounts of pressure. It's part of our daily life, and we don't even really notice it because we've grown up with it all of our life. All right, hope you learned some cool stuff, and we'll see you again at Educator next time.